drains, and this bridge was kind of dislocated. And this is in 2018 when the team went out to select the site. So we did do trout hull survey, but not exactly on this phase. And these are road collapses from the same rain event. Now, what is the sediment budget? Does anybody have any idea? Any geology students here? Well, it's basically calculating over time amount of sediment that comes down from bank erosion, yes, from the channel, from two sides, and from upstream. Now, how do you do that? To do that, you would have to regularly perform channel transects, which is like go in the river, either shoot a LiDAR and keep on shooting it up before and after an event, which is expensive, but it is very good high quality data, or fly drone, pre an event, post event. Otherwise, which we did is regular channel monitoring, which is taking equipment, theodolite and all these total stations and doing survey across the channel at several sections. This is what we had done. So the whole activity started with some field site selection, setting up the erosion pegs, doing the channel survey, collecting soil sediment samples from the river section along the river bed, and then bringing them in the field, doing grain size analysis, typical sedimentological studies, sieving them, measuring the grains, then doing a hydrological modeling as well. We are doing the Heck-HMS model for the May simulation. That is why Mr. Wilson knows I keep pestering for flow data. And geomorphological and aerial photograph studies. But we don't have very recent aerial photographs. We have, which year? About in the 60s or 70s. So the sites we selected were 8 sites for channel transects. Now 8 site means 8 location. Now for each location, there may be 3 lines of survey lines, so it's not 8 survey lines. 4 sites for erosion pegs, but 6 now. We select. Yes, 2. This needs to be updated. 6 now. So total of all these points you see over here, these dots are where the channel surveys are done, and the red ones are where the stream flow locations of WRA are there. One is at Rio Mino at Cooper, whatever Cooper. Yeah, there's Pindars at Arthur Seat. There's 2 Pindars stations for WRA. So the plan is to calibrate over here, but I must mention here that when I look back on the flow data, for me, 14, 15, 16, 17 is missing. So maybe something, excess sediment went in the gauge or data loss. So you have to check that. Otherwise it's... So more close-up of the sites where we are doing the survey. And to give you a brief description, if you can describe why we selected the sites. Basically looking areas where past erosion activities have taken place, looking at places which had hurricane terraces. Dr. Miller can explain a little, and then I'll take back.
The first site is in the upper part of the upper Rio Mino Basin, a place called Grantham, or Coffee Peace it's also called. And we've got, it's one location, we've got 3 channel transects there. And the reason why we did that is that in that upper part of the basin, there's a very large floodplain area and a large sediment sink. And I think during the rains there in May 2017, according to the landowner who owns about 300 or 400 acres in that part, said that the entire floodplain was inundated. So I think during a major rain event, that could be a major source of sediment from that floodplain into the stream. Now, between Grantham and our next site is Trout Hall, through the Frankfield area and that part of the Rio Mino, you can see there's a little bit of blank area there where we don't have any transects. And the reason for that is that the channel is mostly there, a bedrock channel. In Cretaceous limestones, and sandstones and volcanics. So we don't think that's going to generate much sediment because it's in a bedrock channel rather than an alluvial channel. Now, coming into Trout Hall, I know many of you are familiar with Trout Hall, and this is a part of the Trout Hall area. Again, that is a large source of sediment and a large sediment sink. But in fact, the eroded slope that you can see there is part of an old debris flow fan, which is now being reactivated. And a lot of this cut was actually exposed and cut and eroded during those May rains. So that is a major source, probably a major source of sediment into the river during flood events. And in the Trout Hall area, again, we've got, there's one location there, we've got 3 transect sites. And then we come down further down into the confluence with the Green River. And again, the Green River, there's a lot of volcanics up in the Green River drainage basin. And it's really the volcanics and some of the what's called volcaniclastic rocks, which are going to generate the bulk of the sediment in the upper part of the Rio Minho. And we have a transect both upstream and downstream of a confluence with the Green River. Then further down, we've got where our Peter showed the flooding damage on an earlier slide. We've got then basically a large area there at Pennants. And Pennants, again, there's a main stream, there's a little tributary stream that comes into Pennants, but it's on a large bend. It's on a large meander bend. And on the inside of the meander bend, there's a hurricane terrace and floodplain there. That's going to be a fairly major source of sediment. So in Pennants, we've got two transects. One just upstream of the meander bend and one downstream of the meander bend. And then further down the river then, our next site is at Mullet Hall. Again, our Peter showed an earlier image of the flooding there at Mullet Hall. And then our last site is, we've got 2 sites basically. One on the Rio Minho just upstream of the Pindars River, which is our lowermost site, and that's just before there's a big bend and it goes then into the gorge, which forms the sort of lower part of the basin. But we've also got 2 sites at the mouth of the Pindars River. And again, the Pindars River is draining a lot of volcanics and sedimentary rocks in a formation called the Summerfield Formation. And so we have the Pindars River, during rainfall events, it floods very rapidly. It rises rapidly. It generates a lot of sediment. So that's basically the explanation of the 7 sites that we have. And we have 15 transects at those 7 sites in total.
So this is going over the more pictures of the sites we selected.
I just wanted to help me understand the correlation between the erosion pegs, the sediments, and the flood.
We'll get to that.
Come into that.
We have 3 parts of the study. One is these 8 sites, you do channel survey. So you do in a pre-rain day, pre-rain period, you do after the rain, you plot them, I'll show them, and you see how much the channel has moved or accreted or whatever it is. Then we have separate sites where we have drilled in erosion pegs. These are metal rods which are on the ground, and they are down on the slope faces at specific intervals. So every month, go down there and take the measurement how much it is above the ground. So there is another set. The third part is the hydrological and hydraulic modeling we are doing with the data from the past rainfall, from the metal. So what he explained is how we selected the sites for the channel survey, covering all kinds of geological rock types, formations, limestone, sediments, so we can, because erosion is different for different types of rocks, right? So that's what we consider selecting them. So yeah, these are some of the sites and so more of these. So if you see here, this is where some of the stakeholders, Adrian, Rohan, we took some of them in the areas to see how the survey was done. This is Pennants. So you come down, this is across from where the flooding happened. this entire, that when he's talking about the bend, this is where the river bends. These are what you call the meandering bends. So you do a survey before the bend, right? And the bend and after the bend. So 3 channel lines around it. And this is the centrally enlarged geological maps, mainly volcanics, volcanoclastics. So our sites covered all kinds of formations to see the bedrock relation to the erosion. Now, to give you how channel survey is done, basically you take these equipment, these are leveling rods, and you look for a benchmark on one side of the channel. You put your equipment and somebody else moves across the channel with the meter staff, and then you read from the theodolite on the other side, and when you plot, you get the channel depth. So these are the data from last year, April. We're showing some of it. We are not showing all the 16 transects. It's not possible. So Dave, you can explain more. This is from Coffee Peace upstream. The top first part of the top is the extreme upstream end of that's Coffee Peace. Then we move it down, and you'll see Trout Hall, much wider.
Well, I'm not sure whether you can see it in the background, but here's the extent. It is a water surface at the time when we took it. This is from April in 2018. So we're really starting our surveys, left bank and right bank, some distance above the main channel, so that our survey pegs don't disappear, and we can find them again and resurvey. And we've done some resurveying of many of these sections again in recent months. Now, I should say that one of the sites, this site here at Dank Savoy, we went there a couple of months ago. We've now surveyed that a 3rd time now, because there were some rains just a couple of weeks ago, and we noticed that the channel had changed a little bit. So for this particular site at Pennant, we've actually done three surveys now already, and we'll do a couple more before the end of the project. But that's what we're doing basically at the 15 sites. Our surveying from the left bank to the right bank, at fairly safe, secure locations above the channel. And from that you can, and then when you overlay, you go to the second survey.
These are all the sets from the first survey.
These are all from the first survey of April, May, June, July 2018.
And you can see the water level is very low because it was dry period. It's still dry, not so next one here. And the red one is now.
These are just to give you an example of the red lines now. The black lines on here are the survey from 2018. And the red line now is a survey from just recently, in April and May of this year, at 2 selected localities, Trout Hall, River Transect number 1, and Ballards River Transect. And what we can do from that is, not getting too deep into the science, we can use a function to look at the changes in the volume of sediments within the channel, to say whether it's a positive change or a negative change. And from that we can build up then a sediment budget. So you can see here, for example, in the Ballards River, there's been a little bit of scar on the right bank, base of the right bank. And that probably overall, we haven't done the maths yet, but probably overall that means a slight loss in sediment in the channel. It's moved somewhere else. So from this you can sort of build up a little sediment budget within each section and then extend it to other parts of the channel. Oh yeah, there's more examples. And by the time the project ends, we'll have probably a 3rd, 4th, and maybe even 5th set of data over time. So we'll be able to look at how the channel has changed over time. Now that's just one aspect of it. Channel change is one aspect of it. That's one side. The next aspect of it really is the
grain size.
grain size.
So, yes, so channel, maybe you would like to know how this will help in flooding, what information. Now, from this data, you can measure the capacity of water in the channel by doing some calculations on the volume of the channel, because without this, you wouldn't know how much volume this channel can hold, and later on that can go in the hydraulic model to see if the rain from last year was enough to fill up the channel or spill. If it spills, you will have flooding for obvious reasons, like a tumbler, so how much water it can hold now and if the channel moves. So when we do the survey, we collect sediment samples, all along this channel. So from, let's say you're doing the survey from left to right, so at specific intervals, you pick up the grains, you measure the B-axis or the long axis of the grains, and that's called armor and sub-armor, which is trying to see what kind of materials are in the channel bed. Because if it's upstream, you'll get more coarser materials, boulders. The midstream, less and more rounding of the grains according to the common principles of erosion and transportation, all these technical terms. Basically, movement of grains against each other and friction. And we are not doing the lower Ryukyu there, you will see more sand and silt. So what are the sediments now? So we brought back some of them and then we sieved them into different grain sizes using the sieves we have, and most of them are within the sand, gravel, silt, sand, mostly gravel sizes over here. This is a traditional plot which we use to classify grain size. Now, then I'm going to do some hydrological modeling of it just to simulate what was the flow from the 2017 event, because as you know, we don't have data for all the flow data for all the sub-basins and so on. And this is done by rainfall runoff. Basically, you take the rainfall, you take the slope of the area, the properties like soil and land use, and I'm using the soil data and land use from the 2001, the old land use. I've requested the new land use. Haven't received it yet, so we must on that. And a simple open source model, HMS, which computes it. So we use the DEM. The DEM is from NSDMT, which is the 6 meter and horizontal and 1 meter vertical. From that you extract the catchments. Now, if for those who are working with hydrological modeling or have seen the DEM would know that there are gaps in the data, especially on flat areas. So the transects we've done for these 68 locations, it would be good to remove the data from the DEM for those locations and put in the channel data and combine the two to create a new DEM so that your elevation gets accurate. That can be done in GIS, so that's the plan to do it. And then use the soil data, land use, generate the runoff friction coefficient using a traditional method. This is commonly used and in the US, and it has been done in Jamaica too, the SCS method. Now I did a prelim run with the rainfall data from the Mason River Automated Weather Station for the May rain, and there was for those of you who have seen the previous presentation, there was a little bit error which is calculated now. It's 241 millimeters what I got from the total 7 AM to 7 AM. That is how you all do the AWS data calculations. So I use the rain rate, rainfall depth, sorry, not the rain rate. And this is the prelim run of the flow, peak flow. It's gone up to 450 for just this point over here, Cumet. Now, ideally, to make this model work and calibrate, you would need the stream flow data at Coupois and then calibrate the flow from this with the flow that happened in the May rain to see, and then use that flow in the channel to see the capacity of the channel and so on. That's another aspect of it. And the third aspect is the setting up of the erosion sites, which are 6 now. And Rupert can explain more on this part. Rupert?
Afternoon, everyone. So I'll go straight very quickly, not to get into the technicalities, but to give you a brief overview. So we have 5 sites at the present. We are going to do a next site because we want to see, we have literally covered most of the, what I call it, soil that are sensitive to erosion. And we have a next soil type or rock type that is, we want to see what's happening in that rock type. So that's the one, Granta. So that's the last one, which is somewhere over here that we need to cover. So we are looking at Dan Savoy, Ballards, Green River, Coxswain, and Pindards. The reason why we selected these sites is because, one, the geology. So what we need to factor is our source, which is our geology, which provides the soil material that you need. We also need to factor topography, so we want to be looking at hill slopes. We also need to factor land cover, so we want to factor areas that we can see bare soil, the areas that we see trees, where we can access the areas that are mixed between your bare soil as well covered with some vegetation, and areas that we get some amount of what we call human activity, where humans are modifying the surface. And that's the last one, where we have land management. So land management part is the worst part, because humans are never nice to the environment. So that's the challenging part. So but we try to incorporate that into our analysis. All right, so at dams, we actually have 3 sides of dams. And this is along what I call a gully, and so the pegs are here. They're not that visible because it's overgrowth at that time. But when during the drought period, there's literally no vegetation. And as it rains, the slopes will lose its integrity and it will erode. So we install pegs and leave, I said, 20 centimeters out. And after each rain event, or every month, if it's possible, we actually go back to the site to see how much movement occurs. So you want to see whether there is an increase or decrease. It doesn't matter if it's increase or decrease. It still means that erosion is going on. And that's something that we realize that sometimes you actually have an increase in the amount of exposure of your peg, and sometimes there's a decrease. What the decrease means that erosion is occurring up top, and it's being deposited on the peg itself. But that also includes that there's erosion going on. So it's not just looking at just increasing your peg size or what is proposed. So this is dams and 3 sides. We have to design how we actually peg the land to cover as much of the slopes and capture as much of it as possible. So we have to design. So normally you're expected to see a grid shape across your surface. But because the land is irregular, sometimes you have to modify your pattern or design to suit the topography. So dams, if we look, there's not much movement, but in some cases you're actually getting some amount of movement. This site was chosen by Dr. Miller and the team. And when they first visited the site, it was all bare soil. And after a few events of rain, actually, you start getting vegetated. So by pegging, you can actually see what the effects of vegetation actually has on the erosion of this surface, of this site. And when it becomes, lose all its vegetation again, because actually there's actually cows in it and animals in the area, so they will actually disturb the vegetation. And we can actually see what role that plays as well. And that is part of understanding the land management side. So this is where you actually have to modify how you design the peg, because there are small topographical changes along the surface. So how you design your pegging, and you have to modify it as you go in the field as well. So we see we try to capture the slope, so that's the factor in erosion. So the geology which produces soil, so you have to peg different locations where you have different soil types based on the geology coming out. And then you want to capture your slopes, which, because of gravity and grade, those areas will be low. So those are areas that we try to capture. So, alright, so Ballards is an interesting one, because Ballards is where you can actually see erosion going on from one day to the next. And we'll see, so this is one of our pegs, and this is our 20 centimeter. So that is what was exposed, and now we can see it has moved. So after we did the site, after the yard and grading, then there was some amount of movement. And in some of the locations, the pegs are actually removed totally out. So there was enough erosion going on that it eroded the peg. We're not sure if it literally eroded all the peg down to that distance, or it was enough erosion for the peg to lose its integrity and fall out. So that's something we have to factor in as well. So, and you're getting deep gullies are really being formed in artistite. So, and also you having burials of the pegs. So even though they are on the same slope, the material is coming on and the pegs actually being buried. So we literally, so this one is almost close to being buried. So the idea that we have is to, at each time we see burials of pegs are close to being buried, we will reset it to 20. So we can always have those pegs being exposed. So at each visit we know how much material is being deposited or eroded, and then we reset it for the next visit. So we have a control. And sometimes you have what you call a duality, so pegs that are confused. So you have in deposition and erosion. So at one event, you have deposition, then you have the next event which followed, and there's erosion. So it's a complex system where you have erosion and deposition happening within a short time period. The beauty about having all this side peg is that we have installed an automatic weather station in close proximity to where we're pegging the site. So we can actually do a correlation of what is the weather system, the amount of rainfall is being produced, as well as the erosion, so we can combine those data so we can actually use it in our modeling. If we don't know how much rainfall is produced in the erosion, then we really don't have any idea of how much material is being lost due to rainfall.
And the two weather stations, one was at Edwin Allen, and the other is in Clarendon College. We got the data for Edwin Allen, the March, April, May data. We'll be waiting on data from Clarendon College as well. This is automated weather station, so you have precip, temperature, Tmax, Tmin, specific humidity, all the solar influx, all kind of, which comes in this console. And unfortunately, this is not live fed, like coming to our server or anything, so the Met Office has to physically go and download and give it to us. So that part. So that's pretty much what we are at, and some interviews we did with the people. It's not going too much, we are running out of time. That's